All right. Officially, the session is going to start, so let's go ahead. Welcome to the session on intermittent demand. I will be chairing this session, and I will also be the first presenter. So I suggest we just get things started. Let me see if I manage to share my screen with you. All right, can somebody say if they can see my screen?
It is visible.
Yes, okay, perfect. So my name is Sarah van der Auraar. I'm a postdoctoral researcher at the MIT Scale Center in Luxembourg at the Luxembourg Center for Logistics and Supply Chain Management. And I will be presenting to you today my latest work, which is about periodic intermittent demand forecasting. And this is shared work with my co-authors Thomas van Pelt and Joachim Arts, who are also both working at the University of Luxembourg. So needless to say, in a session on intermittent demand, that, well, intermittent demand can be quite difficult when we're talking about forecasting, and also especially when we're talking about inventory management. Now, what we have found in data from practice is that actually time between demand events is very often not memoryless, unlike what is typically assumed in forecasting models. But instead, it can display some sort of periodicity. Now, what we have found in dealing with this is that using this information on this periodicity on the time since our last demand observation can actually be an important predictor for future demand. And if we incorporate such information in an inventory decision-making system, we can greatly reduce our inventory costs. Now, what we find, what we can also show is that a state-dependent base stock policy is optimal under such circumstances. So being in a session on intermittent demand, I probably don't have to explain to any of you that intermittent demand is a very common problem, something that is very often observed in practice. It's something that we can see when we're talking about manufacturing, when we're talking aerospace, spare parts, petrochemicals. All of these sectors oftentimes experience intermittent demand. And now what makes dealing with such demand difficult is that there's two pieces or two facets of uncertainty in this demand. The first one is the obvious one, what will be our demand size, that is unknown. And the second one is the uncertainty in the arrival of a demand. When will demand occur? And of course, dealing with these uncertainties is quite a challenge for forecasting and also for inventory management. Now, seminal work in the area of intermittent demand forecasting, very well known to probably all of you, is the work by Croston. And Croston, what was his great idea to estimate intermittent demand into two pieces, exactly the two that we discussed before. That is, on the one hand, the size of a demand when it occurs, and on the other hand, the interdemand interval. And the idea of Croston was to forecast those two pieces separately and then to recombine them into one forecast, into one number. Now, an important assumption that is made by Croston in his work is that the occurrences of the demands are Bernoulli distributed. And this means that the interdemand intervals are geometrically distributed. Now, being geometrically distributed, this means that those intervals are memoryless. And it is exactly this assumption that we are questioning in our work. Because assuming that the interdemand intervals are memoryless also implies that if you make a forecast, that it will be a forecast with a constant probability of a demand to occur in the future, as there is no impact of the time that has passed on the probability of observing a new demand. Now, in our work, we actually think that this is not necessarily always the case, and we say that the probability of a demand occurrence can be dependent on the time since your last demand. And if you think, for example, about spare parts, this is actually quite an intuitive assumption. If we would say that the probability of a part to fail depends on the age of the part, this sounds quite believable. And it's exactly this idea that we think is true not only for spare parts, but also for many other types of demands. Now, instead of modeling such behavior then with a geometric distribution, we could, for example, use a beta binomial distribution, such as the example that you can see here on the slide. And so what you can see very clearly is that we have a non-constant probability of observing a demand. Probability is much higher in period 5, so after 5 periods of no demand, than in period 1, when only 1 period of no demand has occurred. So what this also implies is that as soon as we do observe a demand, this probability resets. It means if a demand occurs, we start again with, well, 0 periods without demand, so our probability distribution then shifts. Now, we are, of course, not the first people ever to consider the fact that demand probabilities are non-constant. There are, in fact, many other people who have considered the same idea, but in a different way from what we do. For example, there's ample work on seasonality and cyclic demand, where we have recurrent demand patterns with a deterministic cycle length. The difference with our idea is that in our case, the cycle length is not deterministic, as actually the cycles reset every time a demand has occurred. The idea is also close to the idea of inventory obsolescence, where the probability of a demand occurrence will decrease as the time since your last demand increases. What we have as an idea is actually a generalization of this setting of inventory obsolescence. As for us, it is not set up front that the probability should increase or decrease, but just that it is different over time. In fact, our work is most closely related to the work on Markov modulated demand. So when we're dealing with Markov modulating demand, we actually have a modulating process that influences a parameter of our demand process. An important assumption in this work is that the modulating process and the demand process are considered to be independent. And we actually assume that they are intertwined so that they can influence one another. And in that sense, we are generalizing approaches of Markov modulated demand. So let me give you some notation to describe the problem that we are dealing with. So we define here a random variable h, which is the size of a demand when it occurs. And we have a random variable t, which expresses the time until our next demand occurrence. So this is, as you can see, basically the same idea that Croston had in his seminal work. That is, we're going to split up our approach into 2 pieces. That is the size of a demand and the time of this demand occurrence. Now with our random variable t, we determine a hazard rate ht of y, where y is the number of periods since our last demand observation. And with this, we can express the probability of observing a demand today, so after y periods, given that our last demand is y periods ago. And this is what we call our hazard rate. Now, using our random variables h and t, we can express a random variable d of y, which is the demand occurring after y periods with no demand at all. So we can express the probability that our demand in a certain period is of value k, using both the probability that the demand will occur and that it will be of size k. Now what we want to do, as I said in the beginning, we're looking at forecasting for intermittent demand, but we're also looking at inventory management. And for that reason, we are proposing here an approach that is actually an integrated approach where we combine both the forecasting and the inventory management in one. And for that, we will formulate our problem as a Markov decision process, where we consider a simple setting, a single echelon inventory system with periodic review, lost sales, and a lead time of 0. So really a basic setting to explain the general idea. So you can see here on the slide the optimality equations V of x and y, where x and y denote our state space. X is the inventory at the beginning of a period before we place an order, so clearly related to our inventory problem. And y is the number of periods since our last demand occurrence, which is clearly related to the idea of intermittent demand. So what we can see here then in the optimality equations is the expected total costs. What we want to do, of course, is to minimize those. And if I say minimize, well, we have 2 pieces here. We have the immediate costs. We have C that consists of penalty costs, P, and holding costs, H. But we also have expected future costs, which are related to, well, what happens after this period, after our decision, after maybe a demand occurs, maybe no demand occurs. So what we want to do is we want to find an optimal policy that will depend on the time since our last demand, so on Y, that minimizes our expected future costs. Now, so what we are going to do is at the beginning of each period, we are going to review our inventory position. So what do we have in stock right now? And the number of periods that are there since our last demand. So how many periods without demand are we having at the moment? And then what we do is we find our value A. A is then our order up to level using value iteration. Now, concerning this value A, our order up to level, we can formulate two theorems concerning its properties. And our first theorem tells us that a state-dependent base stock policy is optimal in each period of the finite horizon problem. This means that in each period, we can denote a number A that is dependent on this Y, and that this is an optimal solution. Now, proving this first theorem is quite straightforward, as it just involves showing that our value function presented here is convex. And the second theorem, that's a bit more involved. Our second theorem tells us that if our demand hazard rate, ht of y, so our probability of observing a demand in period y or after y periods, given that we are now y periods since our last demand, well, if this is increasing in y, then our optimal base stock level, which is state dependent, is also increasing in y. Now, we can also prove that this is true, but this is not a straightforward proof because it involves showing that our value function, given here on top of the slide, is submodular. Now, the big problem here is that it's not component-wise submodular, meaning that it consists of 3 parts that we sum, and not all of those parts are submodular. So what we have to do is we have to use slack on submodularity of some of the parts and use it to compensate for the lack of submodularity in other ones. And this is quite complicated, so I will not go into any details, but I just want to let you know that this was quite a pickle to, to go through when we were working on this paper. So far for the technicalities, I would really like to illustrate the idea that we have in a small numerical experiment. So what we have done is we have actually created a setting in which we enforce this kind of periodicity in intermittent demand, and have then compared the performance of a number of methods to see if there's even anything to gain using such a complicated approach. So what we have done is we have compared the approach that I just discussed, so using the Markov decision process. We compared this with 2 well-known state-of-the-art forecast methods when talking about intermittent demand. That is Creston's method and the synthesis-Boylan approximation. So both of those require smoothing constants, which we optimize using the mean squared error. And both of them, well, they produce a point forecast. So we translate this point forecast to an inventory decision using a negative binomial distribution, which is quite commonly done in literature. Then next to forecast approaches, we are also comparing our method with inventory approaches, as we are going for this integrated idea. So we compare our performance also with a base stock policy, where this base stock policy has a fixed base stock level, so a fixed order up to level that is dependent on our distribution of the demand sizes H. So this means actually that this base stock policy assumes there is no intermittency and there's just demand in every period. And we use the optimal Nussbender fractile to set the base stock level. And then lastly, we compare our approach with a state-dependent base stock policy. So here we use the distribution of the demand d of y, so it's state-dependent depending on y, to again determine a Nussbender fractile. And this last benchmark is in fact a myopic variant of our own approach, as it only looks at minimizing your immediate costs C and not at the expected future costs. So what we do is, as I said, we set up an experiment that explicitly violates this assumption of memorylessness. So we generate inter-demand intervals using a beta binomial distribution with 3 parameters, which is clearly with changing probabilities of observing a demand. We generate demand sizes using a discrete Weibull distribution, and we split our data set then into an initial data set and a test data set, and set inventory parameters, penalty costs of 5 and holding costs of 1, just to illustrate the performance. So here you can see a little bit of an overview of our numerical evaluation. So we've done 10 settings, so it's just a small experiment to show you our performance with some demand characteristics that might be familiar to you, the average size of a demand, the average demand interval, the average demand per period, and then the coefficients of variance of the size and the intervals. So here what you can see is the results of our experiments, which are expressed in percentage gap. So it's the percentage gap in total costs of the 4 benchmarks compared to our MDP approach. And what we can see looking at this table overall is that the MDP approach is outperforming all of them. So this is good news for our approach. Now, if we look a little bit more in depth, we can see in column 2 and 3, Croston and SBA, that the MDP is greatly outperforming those two. And this is not a big surprise, as we explicitly generated our data to violate the assumption of the memorylessness that Croston and SBA use for their forecasts. So it makes a lot of sense that our MDP is doing better in this setting than Croston and SBA. Then in the 4th column, we can see the performance relative to the news vendor approach. And again, we can see that we outperform this one. Again, this makes a lot of sense because the news vendor approach assumes that there is demand in every period and completely ignores the intermittence that is clearly there. And then a very interesting column is the last one, where we use the true demand news vendor, so the news vendor fractile of the true demand distribution. And we can see that, well, we still outperform this method, but the gap is quite small. So what should be the takeaway from this is that while using this information on why the number of periods since our last demand in the inventory decision-making clearly gives you cost reductions. Even if you only do it in a myopic way, as in the last column, we already can see great performance differences with the other methods. So for me, this shows that there is great potential in using such information for forecasting and inventory decision-making. So in conclusion, as we said, well, dealing with intermittent demand for forecasting and inventory management can be quite a challenge. And especially now that we see that more is going on than what is traditionally assumed in literature. For example, there could be periodicity present in our demand occurrences. So what we found is that using information on this periodicity and on the time since our last demand occurrence can actually help us to better predict and to better manage the inventories of the items that have this kind of demand. And we can show that a state-dependent base stock policy is optimal under such circumstances. And with that, I would like to conclude my presentation, and I'm very happy to take any of your questions.
Hi, Sarah. Thanks very much for that presentation. I thought it was really interesting. So thanks a lot. I just wanted to ask you a little bit about the regularity of this periodicity. Did you assume strict periodicity, in other words, exact periodicity? And do you have any feeling for what would happen if there were periodicity, but it were weaker and it was less exact? Let me put it in that way.
That's a very good question, John. Maybe I should have explained this more clearly, because indeed we've investigated both. So because if your demand is strictly periodic, basically, well, and we know this, then it becomes quite easy to forecast. But what we have done actually is we have used a distribution to express this periodicity. So for example, there's an expected time between demands of 8, but it could vary between, let's say, 4 and 14 or something like that. So we've really also investigated this uncertainty in the occurrences.
And what did you find when it became more uncertain? I mean, one would expect the benefit to be less. I'm just interested in the feel for it.
So we are let's say in the beginning of the numerical experiments, because this is very recent work. So what we found up until now is especially if the time becomes longer, so our expected time between demands becomes longer, then we start performing really well. Because then there's actually a long period where there is not much happening, and then we have an increase in probability. So in such circumstances, we see great potential for approaches such as this one.
Thanks again. Great presentation, Sarah.
Thank you very much, Sean. All right, in the meantime, I will already start setting up the presentation of our next speaker, because it's a recorded one, but please, if you have any more questions, let me know. Okay, if there are no more questions, then I suggest we continue with the next speaker. So the next speaker is Hans Levenbach, and he has sent us a recorded presentation, which I will play for you now. And it is, well, as we are in an intermittent demand session, also on forecasting with intermittent demands, a new approach.
My name is Hans Levenbach. My talk is about forecasting with intermittent demand, a new approach in collaboration with Isos Santos Costa. Almost 3 decades ago, in the International Journal of Forecasting, there was a number of articles on forecast accuracy measurement, and these authors had some comments in it that I want to refer to. Robert Files, who was an ex-president and editor-in-chief of the journal at the time, said, "The signal failure on the part of statisticians to respond to the model-building failures identified in many empirical studies on forecast accuracy measurement has not been resolved within the forecasting profession itself." 2 other authors, both associate editors of the journal, and Robert Winkler was an ex-president as well, said the focus in forecast evaluation should be shifted from a measure-oriented approach to a distribution-oriented approach, in which distributions are primary and other measures are viewed as summarizing different aspects of the distributions. A third author, Dennis Alberg, who was also on the editorial board of the journal, said a particularly sobering finding is the poor performance of the root mean square error. The reliability of the root mean square error is poor in forecasting, and it is scale dependent. Most of these issues are still hotly debated among these researchers. Now I want to talk about a new approach to intermittent demand forecasting, taken into consideration some of these comments. It's a 4 or 5 step process. The first step is an important data exploration of the interdemand intervals, the intervals between demand values, and data quality checks for unusual variation. Then we go into determining the empirical interdemand interval distribution for the zeros and define a lag time interval, zero interval, LZI, conditional on the interdemand distribution. Validate the independence between the LZI intervals and the non-zero demand volumes. Third step is to sample these empirical LZI distributions and make projections over the desired lead time. Make enough projection over the desired lead time. Each lag time zero interval is followed by a non-zero demand value or volume. Then we need to validate the independence between the LZI intervals and the ID demand volumes, because in the currently used Crossan methods, it's assumed that these intervals and demand volumes are independent. The measure to measure that independence is the so-called Kullback-Leibler divergence, as a measure of distance between 2 distributions. The methodology is based on coding these data profiles into what I called alphabet profiles that have the properties of discrete distributions. As an important data exploration step, we want to check the data quality before we make any forecasts. The spreadsheet table shows demand series for a stock keeping unit and location in a population health forecasting application at a New York City area hospital from January 2015 to April 2018. The next 20 months are used as a test period so that the results can be compared with the actuals for this period. We are then asked to make a lead time demand forecast for the year 2020. Similar data may be seen for hospital admissions in virus pandemics, for example, retail sales at doors in different regions of the country, and more commonly in spare parts inventory applications. In exploring the nature of interdemand intervals in relation to the distribution of non-zero demand sizes, it may be surmised that for longer interdemand intervals, the intervals between the non-zero demand sizes could be increasing or decreasing in size over time. There is this dependence, possibly. In this data set, there are 3 lag time zero interval durations. For example, the first LCI interval has 1 0 preceding the demand size 211. The next LCI interval has 2 zeros preceding the demand size 458. And the next one has none, and so on. If the process started in January 2015 with a new product introduction, for instance, we could add demand size 390 in the single zero lag time zero bucket. Before creating any models for intermittent demand, a forecaster should first consider the validity of assumption of independence made by the traditional CrossFit methods by examining the historical data in a real-world context. The step 2 is to determine the interdemand interval distribution. Each demand size is preceded by an interval of zeros. Adjacent demand sizes are separated by zero lag time interval. I denote by LZI _0 in this data set. There are 3 LZI intervals with the following distribution. LZI 0 has 10 occurrences, LZI 1 has 6 occurrences, and LCI 2 has also 6 occurrences. Thus, the empirical frequency distribution for demand size given LZI is shown in the left panel, and on the right panel we show the conditional distribution for log demand size given LZI. For these larger numbers, it's not uncommon to be taking logarithms. As for making one step ahead projections of the demand volume following a lag time zero interval, we see that by making the simplest, even the simplest projection of averages and medians, and there appears to be a significant difference between the 2 0 intervals and the other 2. The LZI _2 intervals appear to be followed by larger demand sizes on average, in this case, than the other 2 lag time demand intervals. In step 3, each interdemand interval is followed by a demand size. Our measurement model is analyzed in terms of the logarithms of the original demand sizes. So we display the distribution of demand sizes by LCI intervals in a box and whisker plot, or simply a box plot. The box plot is a simple method for graphically depicting groups of numerical data through their quartiles. Box plots may also have lines extending vertically from the boxes called whiskers, indicating variability outside the upper and lower quartiles, hence the term box and whisker plot. The 3 distributions corresponding to each interval size are not the same. The middle one has a thicker tails than the first one, and the third box depicts a skewed distribution. Examining the data in this way differs from the Crossan-based data generation method in that we do not assume that intervals and demand sizes are independent based on examining the data in a real-world context. The independence assumption does not appear to be commonly validated in cross-syn applications to intermittent forecasting, so we'll take that up here also. Now we need to create some point forecasts for the zeros, and we do that by forecasting them by interval size. The multi-step forecasts are not assumed to have a level or flat forecast profile. In our example, we can start by using an overall mean, median, or actual naive on an average, the most recent 3 demand sizes. The typical projection can be obtained by averaging as an average projection and can often outperform an individual projection. Exponentiate the individual projection to obtain a typical typical non-zero demand for each interval size. We create enough of these interval projections to cover the lead time or planning horizon. By sampling the LZI distribution as an EARN model, we obtain multi-step interdemand intervals. Each projected interdemand interval will be followed by a projected demand size associated with that interval. The EARN model in this case would contain 22 colored balls for the forecast horizon, each color associated with an interval duration. 10 blue balls for LZI 0, 6 orange balls for LZI 1, and 6 gray balls for LZI 2, say. In the sampling process, a ball is drawn from the EARN, a color is noted, and the ball is replaced in the EARN is shaken, and then another ball is drawn, etc., until the forecast horizon of 20 months is covered. These are all programmable steps. So we create a forecast profile as needed. For example, in this case, we consider a sampled sequence of interval sizes to cover May 2018 through December 2019. Each interval is followed by a demand size. So in this example, the projected intermittent demand profile starting from May 2018 is depicted in the spreadsheet. You can also examine intermittent data at different frequencies. In this example, in inventory, there's 52 weeks of inventory demand volumes with only 14 zeros scattered throughout, and the rest are non-zero. The demand volume in each interval, associated with each interval, is 57 for the LZI_0 intervals and 12 for the LZI1 intervals and 4 only for LZI2 intervals. You can see the numbers are small, just in a typical inventory type application. What we do now next is for each LZI interval, we divide the total volume into each component to arrive at what's called an alphabet profile. So in the first column with the total of 57, I divide 57 into each one of these numbers, and so I get fractions that add up to 1. Likewise for the second column, and likewise for the third column. These alphabet profiles will be used in constructing information theoretic validation of independence. We see here that we need to calculate an expression involving the joint alphabets and 2 marginal alphabets. This measure is called the mutual information measure, and it goes by the name of the Kullback-Leibler divergence measure. It has some very good properties in that it's always positive, and we get equality if and only if the marginals are equal to the product of the marginals equals the joint. Down below, I will show you next what that looks like. I won't go into the details here. I depict what the 2 alphabets look like. The top alphabet is the joint alphabet of the intervals and the demand sizes, The sum of these points add up to 1 in both of the graphs. But you can see there are some differences in the profiles, in the patterns. And that is being measured by this Kullback-Leibler divergence measure. In this case, the answer is it comes out to 0.56, which suggests a lack of independence. The underlying theoretical underpinnings are derived from the structured inference-based SIB model, a modeling approach that's algorithmic and data-driven, in contrast to the conventional data-generating modeling approach with normality assumptions. In this particular example, which I won't be able to go in details, was reported on in the symposium in 2004. In summary, the underlying theoretical underpinnings behind this intermittent demand forecasting is a non-Gaussian, data-driven, algorithmic modeling approach called structured inference-based, SIB. And it's applicable for regular and lead time intermittent demand forecasting applications, and based on validating, firstly, the dependence assumptions made on demand size and demand interval distributions, which tends to be missing from the Croston methods, which assume independence. Secondly, using sampling techniques to sample the underlying empirical distributions used to forecast the lag time zero intervals, and noting that each interval is followed by a non-zero demand from a conditional demand distribution. And thirdly, the independence or lack thereof can be measured with a mutual information measure called the Kullback-Leibler divergence, which is a generalization of mean square error. Intermittent demand forecasting has now been added in a revised edition of my paperback book, Change and Chance Embraced, as well as other topics as they come along, including the Professional Development Workshop Manual, both of them available on Amazon.com worldwide. Well, thank you very much for your attention.
All right, thank you everyone. This was the presentation of Hans Levenbach. Hans, I don't know if you are with us at the moment.
I think the co-author is here.
I don't know if there are any questions regarding the presentations for the authors. Oh, and I'm so sorry, I'm just seeing the chat. I couldn't read it while sharing my screen, that apparently the slides were not coming through well. So I really apologize for that. I don't know what was causing this issue. Okay, but in case there are no further questions, Oliver has greatly offered to share the presentations from his computer now. We'll see if this solves our issue. Then, well, we still have 1 minute to spare. But maybe, Oliver, you can already set up for the next presentation. So the next presentation will be by Marius Dossin, who is here. So he's here to answer questions also after the presentation.
Yes, I'm here. Hello, all of you.
Hi, Marius. Thank you for being here.
Should I start?
Oliver, I think we can get started. Thank you so much for helping out.
Okay, no problem.
And apologies again.
Hello, my name is Mariusz Dosin. I'm working in the Department of Econometrics and Statistics in the University of Szczecin in Poland. Today I would like to talk about biasedness of forecast errors and intermittent demand perspective. Main hypothesis of my research is that exposed forecast errors are different with respect to their biasedness. Biasedness is usually related to forecasts themselves, but not to forecast errors. Biasedness of forecast errors is essential in the context of intermittent demand forecasting. The main problem in this research is that exposed forecast errors such as mean absolute scared error or mean absolute error favor underestimated forecasts, sometimes even zero forecasts. On this slide, notation is explained. As you can see, it is very conventional. I would only like to add that n is a number of in-sample values and h is a number of forecasts. Let me present the main point of my considerations. On this slide, definition of unbiased forecast error is presented. According to this definition, the forecast error B is unbiased if it reaches optimal, usually minimal value for unbiased forecasts. As you can see, this definition is also written in a more formal way by using mathematical symbols, but the content is exactly the same. To make the presented definition more clear, now I will discuss the biasedness of chosen forecast errors. At first the basic ones, such as mean square error, and later errors more useful in the intermittent demand context. Mean error is by definition unbiased forecast error because it is optimal and equal to zero only for unbiased forecasts. Mean square error is also unbiased forecast error because it is minimal only for unbiased forecasts. For stationary time series, mean square error is minimal only if forecasts are on the mean level. Therefore, forecasts are unbiased. For non-stationary time series, the expected value of a predicted variable should be related with time, and conclusions are very similar. Conclusions are different in case of mean absolute error. This error is based on absolute deviations between empirical values and forecasts. For asymmetric distributions, mean absolute error is a biased forecast error because it is minimal for forecasts on the median level. As you can see, for asymmetric distributions, median is different than mean, so mean absolute error is minimal for biased forecasts, and this makes this error biased. The previous errors are very basic and are not useful for intermittent demand forecasting systems. Forecast errors for that kind of forecasting systems should have some features. They should be always defined. for intermittent demand data. So, for example, division by 0 is excluded. They should be scale independent and also unbiased. The last feature is my suggestion. In this research, I will analyze 3 that kind of forecast errors. It will be mean absolute scaled error, one of the mean-based errors, namely the mean-based map. The last one, root mean square scaled error, is my proposal. Maze, mean absolute scaled error, is a very interesting forecast accuracy measure. It is scale independent and is almost always defined for intermittent demand data unless all in-sample values are the same. However, Maze, like mean absolute error, is a bias forecast error because for asymmetric distributions, Maze could be minimal for biased forecasts. Maze is minimal if forecasts are on the median level. However, forecasts on the median level are biased for asymmetric distributions, and this makes that Maze is a bias forecast error. Many mean-based errors could be defined. In that kind of errors, instead of actual values, we have in-sample means, which are compared with forecasts. If we take as a single forecast error difference between in-sample mean and forecast, mean-based map is by definition unbiased. However, this might not be true for normal forecast errors, where actual values are compared with forecasts. The last discussed forecast error, root mean square scaled error, is my proposal. As you can probably see, this measure is very similar to Maze, mean absolute scaled error. The only difference is that root mean square scaled error is based on squared deviations between actual values and forecasts. Root mean square scaled error, like mean square error, is unbiased forecast error. It is because it is minimal for unbiased forecasts. In the empirical example, I will use, among others, Croston's method and TSB method. Croston's method is probably the best known intermittent demand forecasting method. In this method, simple exponential smoothing is applied separately to non-zero demand and inter-demand intervals. The adjustment takes place only if non-zero demand appears. On this slide, you can see the formulas. TSB method was proposed by Teutner, Synthetos, and Babai in 2011. It is similar to Croston's method, but instead of interdemand intervals, we have Say's probability, which is better because Say's probability could be updated also in periods with no sales. In the empirical example, forecasts were calculated for 10 weekly intermittent demand time series. First 205 weeks consisted in sample values, and the last 5 weeks are out of sample values. For the last 5 weeks, exposed forecast errors were estimated. Presented data come from a warehouse center selling mostly tools and work clothes. Now you can see weekly sales quantity of a sample product. In Table 1, there are basic information about analyzed 10 intermittent demand time series. These are in sample values. As you can see, sometimes number of observations was below 205, so for some products, sales history was shorter. Sales frequency, defined as a share of weeks with positive sale, was below 40%. This is why median sale for all products was equal to 0. In the last column, there are maximal values, which indicate the presence of outliers. In the empirical research, the following forecasting methods were applied: average, median, which could be identified with 0 forecasts, Croston's method, and TSB method. Average and median were taken as benchmarks. Average is totally unbiased forecasting method in this research. On the other hand, forecasts on the median level are highly underestimated. To remind you, median sale for all products was equal to 0. In Croston's and TSB methods, smoothing factors were equal to 0.1. First values were taken as starting ones. In this table, the results for all 3 forecast errors are presented. To remind you, in this research, average method is totally unbiased. It is because out of sample means for all 10 products were equal to in sample means. With respect to the first error, mean absolute scaled error, 0 forecasts are the best. The results for remaining 3 methods, TSB, Croston's and average, are worse and very similar. Mean base MAPE, by definition, was equal to 0 for average method. It is because out of sample means were for considered products equal to in sample means. Mean base MAPE, also by definition, was equal to 1 for 0 forecasts. The results for TSB and Croston's methods were close to 0. According to the last error, root mean square scaled error, Average is the best forecasting method, and zero forecasts are the worst. The results for Croston's and TSB methods are similar as in case of average method. So these conclusions are correct. Let me go to the conclusions. Many economic variables are asymmetric, usually positively skewed. Intermittent demand is an example. If median is lower than mean, errors based on absolute deviations favor biased, usually underestimated forecasts. It is because measures based on absolute deviations reach minimum for median. If forecast variable distribution is skewed, errors based on squared deviations should be rather applied. It is because they reach minimum for forecasts on the mean level. Hence they are unbiased forecast errors. For intermittent demand data, forecast errors should be always defined, should be scale independent and unbiased. Among 8 forecast errors which were analyzed in this research, only 2 of them fulfilled these requirements. It was mean-based MAPE and root mean squared scaled error. Thank you very much for your attention.
Thank you, Marius, for the presentation. We still have some minutes left for questions, so if there are any questions from the audience, Professor Dustin is here to answer them for you.
If I may say something, I would like to add that yesterday I saw that Professor Hindman has already applied root mean square scaled error. I didn't know about it, so I would like to add this.
Hi, Marius. John Boylan here. I just have a quick question for you. You divide your measure divides by the mean squared error of the naive forecast, which is what happens in MACE. Another proposal, which was put forward in 2015 by Fotios Protopoulos and Nikos Karentzis, I'm not sure if Nikos is still on the call, did something similar, but divided not by the squared error from the naive, but it's just by the mean demand. So it took the error, it divided by the mean demand, and then squared it. So got back up to this squared property, which, as you say, is desirable. I just wondered if you come across that, or whether you had any thoughts about dividing by the mean demand instead of dividing by the squared errors from the naive.
Thank you for this question. Of course, I have also applied this kind of errors, but for some time series, means were very small, very almost equal to 0, and it makes that these errors were very inflated. So this is why I would rather use in my research and my forecasting system that kind of error. When I'm comparing forecasts with naive forecasts.
Okay, thank you.
Again, thank you very much for the presentation. And I think then we can move on to the last speaker of this session. This will be Alex Hallman, who will be presenting on probabilistic forecast for intermittent demand. And as you can see, this is also a recorded presentation. which again will not be shared by me, but by Oliver, to hope that the quality remains stable as it is. So thank you very much, and let's get started.
Hello, my name is Alex Halm, and I'll be talking about flexible probabilistic forecasting of intermittent time series using deconvolution. Intermittent time series are time series that have sporadic behavior. So unlike standard time series, where we use standard time series methods to fit them, those standard methods don't normally work with intermittent time series because of their sporadic nature, and they're also usually low volume. Historically, there have been some very successful methods at modeling intermittent time series. One that comes to mind is Cruston's method, which was originally proposed for point estimates, and for prediction of probability distributions, what's normally seen as a Poisson distribution or negative binomial distribution, which are both also very effective at predicting intermittent time series. There's also kind of this other idea with forecasting. There's methods that fit locally, which is one method per time series, and there's also these grouped methods which pools time series to model future demand. And so what I'm covering today is Efron's G-modeling deconvolution as a global method for modeling intermittent demand. Efron's G-modeling deconvolution was proposed in a paper in Biometrica and also in his book, Computer-Age Statistical Inference. His use cases were around Shakespeare canon dataset, where he was modeling distinct word counts, and also some medical examples. But I wanted to use this method to see how well it fit in with this idea of intermittent demand. And there's a couple reasons why I kind of had reasons to believe that it may be a reasonable method, at least to explore for intermittent demand. First is that it's a empirical based technique, which means that classically in empirical based settings, you have a lot of parallel data, and that parallel data informs your prior. And intermittent demand is exactly that. So companies normally have a large number of time series, parallel time series of intermittent demand. So the first thing that came to mind was, well, could we use this parallel data to inform a prior mixing distribution? So that was the first question. I wanted to highlight two things in this presentation. One was showcase the flexibility of the prior mixing distribution. And I was going to use the M5 data to show that. And I also wanted to show fast fitting and prediction with reasonable forecast accuracy in the parts data set. Okay, so starting off with the M5 data. So M5 was a forecasting competition. It recently ended. The competition was on Kaggle. The goal was to have, you have these 42,686 base time series that are aggregated at various levels. And so there's two tracks. One track was to forecast point estimates, and another track was to forecast quantiles. And not only of the base forecast, but of various groupings of the different time series. The work I'm doing here is in no way replicating the M5 competition. I'm just using the M5 base time series to explore deconvolution. So what's shown here is a table of distinct counts of various demand levels. So there's about 1 million zeros, 387,000 ones, 214,000 twos, and so forth. So what I did here was I pulled all the time series together, and this is part of the process I use to get at deconvolution. So the steps were as follows. First was to pull all the time series data to estimate the general mixing distribution. So xi is the number of times demand was seen, and what we want to know is the distribution of the unseen theta I values. We do this over the support grid. Lambda from -4 to 5, and we use the sample space from 0 to 1051, which was the max demand. I didn't show all the way up to 1051 in the table. I just couldn't fit all the demand on the slide and still make it legible, but there were cases where the demand got that high. And finally, fitting a structure matrix Q with natural spline and degrees of freedom of 6, and this was done with the deconvolver package. And so here's the results. The top plot is the prior mixing distribution, and the bottom plot is posterior draws from that distribution at various levels. So we have a level of 0 for time series that have a very low expectation for demand. We have a draw at 1 that are expected to be around 1 for the demand, a draw at 2, and a draw at 3. And there could be many more draws, but I just wanted to highlight some of these lower demand draws here. There was a couple of interesting properties I saw in these draws. First was zero inflation. And so what zero inflation is that you have two models going on at the same time. One model is predicting how many zeros will occur, and the other model is predicting if there's not a zero, what level is the demand going to be at. Usually that's used with a Poisson distribution. So what we're seeing here, if you look at the top left quadrant of that bottom plot, zero inflation is happening out of the box. I didn't do any work to try to tune a zero inflation model. It's just happening, and that came from learning from the prior mixing distribution. And then when we pull from higher demands of 0, 1, 2, and 3, that distribution starts to move over. One thing that's seen that's very interesting here is the fat tails. And I saw this as a positive because many times you'll have a probabilistic forecast and your intervals are too narrow. But in this case, the fat tails, again, were learned from the prior mixing distributions. And hopefully these fat tails help to be more realistic forecast intervals. So after looking at some of the flexibility property in terms of zero inflation and the fat tails, I was kind of curious how this actually performed in practice. And so what I chose here was a parts data set. The reason I chose a parts data set is because it was originally mentioned, the first time I came across it was in Rob Heineman's book, Forecasting with Exponential Smoothing, the state space approach. And it was also shown in Snyder's paper. It turns out to be a popular data set for assessing the fitness of different methods on intermittent demand. So I have two tables on the left. One is a table of the in sample or the training set, and the table right below it is a table of the test set. And just like I was showing for the M5 data set, the table is set up the same way. We're showing the distinct number of counts for each level of demand, so how many zeros, ones, twos, threes there are. And this was set up the exact same way, or the same fashion as shown in the Forecasting with Exponential Smoothing book. So for details on how to set that up, that's provided in the book. The metric used to evaluate the forecast was the discrete rank probability score. This came from the 2012 paper, Snyder's paper, where he covered intermittent demand models, specifically for probabilistic forecasting. And the code for that, I just showed a snippet here, so it's clear how I'm calculating this. And because this is probabilistic and on a point forecast, I generated a very tight vector of quantiles, so 0.01, 0.02, all the way up to 0.99. And here are the results. So in this data set, to talk about some of the methods, I'll start with the table on the right. The negative binomial method is abbreviated NB. Then there's a Poisson method, deconvolution, deep AR, which was, there was a recent paper, a great paper on deep AR, and the benefits of using deep AR for intermittent demand. And you could set as a backend a general linear model, and what I used was negative binomial in this case. It seemed very appropriate. Z is the benchmark. Z is an abbreviation for zeros, so the forecast on every quantile is 0. ETS is exponential smoothing. Seasonal naive is using a seasonal naive forecast with frequency of 12. The parts data set is at monthly intervals, and so seasonal naive method with frequency 12 seemed natural here. So the first column is mean DRPS, and the second column is seconds, and all the methods are sorted by mean DRPS. So we're seeing that negative binomial performs best, followed by Poisson, deconvolution, deep AR, and so forth. And so what I was seeing here confirmed the same results that Snyder was seeing, was that the negative binomial distribution is an excellent distribution for forecasting on this parts data set. And so my results were very similar to his. Second, what we're seeing is that the accuracy of deconvolution is on par, I would say, with the Poisson negative binomial and deep AR methods. And third, speed. Deconvolution fit 1 order of magnitude faster than the local binomial method, and a little less than 2 orders of magnitude faster than deep AR. Deconvolution fits globally, and this is probably the main reason why deconvolution was so fast, is that it's fit globally as opposed to per series. Now there are other methods that fit globally. A hierarchical full Bayes method would also fit globally, but there's a lot of simulation needed to get long chains that converge, and there's a good chance that that would take a very long time to fit. So it's not just the fact it's fitting globally, but also the fact that it's not using simulations and convergent chains to get the prior distribution. It's using parallel data and splines to fit the prior mixing distribution. So it's a very good bang for the buck. We're getting great accuracy at very good speeds. So I would say it's a very effective model. And you compare that against the negative binomial Poisson and deep AR, it seems to be at least a method worth considering. So deep AR isn't a silver bullet. Of course, there's some things that need to be worked out. So what I showed here was deconvolution essentially in an independent, identically distributed setting. This isn't terrible for intermittent demand because usually Poisson and negative binomial distributions are fit on historical data in a similar fashion. But this isn't expected to perform well, obviously, for time series that are trending up, trending down, or that are seasonal. Anything that is pretty much non-intermittent, what I did here just isn't going to work. Also, covariates were absent, so if there was a covariate that'd be useful for holidays or for marketing data, like promotions, the current presentation I gave right now doesn't have any covariates included, but it is possible, and I'll talk about that a little bit on the next slide. And finally, relevance. So every branch of statistics has its own philosophical problems, whether it's frequentist Bayesian or empirical Bayes. Relevance is kind of the empirical Bayes philosophical / theoretical problem, and the idea is this. So the M5 data set likely had some time series in it that weren't necessarily intermittent, but we included it. Maybe those helped at getting the mixture distribution. But maybe we should have partitioned out the data a little bit better. Maybe we could have done a little bit of work to figure out which subsets of time series would have been most similar or most relevant to estimating a mixture distribution for the intermittent series. But so there's the idea of subsampling, so that's one way to view relevance, but there's also the idea kind of external to your own data set of including any data set. So say, for example, the parts data set, I could have included all of the M5 data in that also to get a prior mixing distribution to forecast posterior draws. So there's the idea of what to exclude and what to include is kind of this struggle in empirical Bayes. It's still something being worked on. So as far as what my focus is going forward, there's a couple ideas here. One is I really want to try using generalized linear mixture models in an autoregressive setting. So it is known that covariates can be used for deconvolution, and I just like to see using covariates, autoregressive covariates, or autoregressive and holiday covariates, autoregressive holiday and promotional covariates, and so forth. The second point is a very specific case. I want to use deconvolution as a back-end replacement for Stan in Slavic's great work on LGT, which is local and global trend exponential smoothing. So he was showing great results on these exponential smoothing models using Stan as a back-end. The problem is that it was, at least his frustration is that it took a really long time to fit these models. So since deconvolution, as long as you have the parallel data to support it, it approaches full Bayes methods, I'm curious if we can use deconvolution as a back-end replacement for Stan and still see some of these great results, that Slavic was reporting, while also being much faster. Third, new item forecasting. This is more just an application area. Because we have a prior mixing distribution, it may be the case that there's some marketing or data where a new product was tested in a test market. If there's an idea of how well that product was performing, we can likely use that information to pull a draw from the prior mixing distribution, have a great forecast for a new item. 4 is more software is needed to make the analysis of deconvolution easier. So first there's a deconvolver package, which is the base for all the calculations. I also have the GEST package, which is short for G-estimation, and it's it shouldn't really be called a package. It's only 2 R helper functions, which wrapped deconvolver to help me iterate a little bit faster for the work shown in this presentation. But more broadly, a lot more software work needs to be done to just make this a lot easier to get through for general practitioners. And finally, more testing with more data sets and also comparing more methods. So what I showed here was deconvolution being compared with Poisson and the negative binomial distribution and deep AR. So the Poisson and negative binomial distribution were fitting locally, and deep AR was the only thing that was maybe similar to deconvolution, where it was more of a pooled method as opposed to a locally fitting method. I'd be curious to see where hierarchical Bayes falls, and seeing how long it takes to fit, and also what its performance is, and of course other methods. References and related work. I only wanted to talk about the first section here on deconvolution. First of all, of course, the book Computer-Aided Statistical Inference has a great chapter on this, chapter 21, where he covers the motivation behind G-modeling deconvolution. And the next 2 papers are written by the author of the Bayes package. The idea here is that G-modeling isn't the only way to get at deconvolution. He uses a non-parametric approach to do deconvolution. And so in those 2 papers he wrote, he compares Efron's G-modeling with his non-parametric approach, and talks about some of the pros and cons. And finally, if you're interested in actually implementing deconvolver or writing software around deconvolution, there's a deconvolver vignette that's very useful to look at. That's all I've got today. Thank you very much.
Okay, thank you, Alex. Again, a very interesting presentation. I don't know if Alex is among us here to answer questions. It seems not from the participant list. So in case you have any questions for Alex, I suggest you contact him via the Wova app or via email to give him suggestions or feedback on his presentation. And with that, I would like to end this session on intermittent demand. Thank you everyone for being here, and thank you to all the speakers and presenters for what they have brought to us today. Thank you very much, and have a good afternoon, evening, morning, depending on where you are, and see you all soon. Bye.
Thank you. Bye.
Thank you. Bye.